Thank you. Thank you everyone for being here, and thank you to the organizers for inviting me. So if you're not familiar with agent-based models, although we've seen some of those actually in some of the talks and posters, and if you're not familiar with digital twins, that's totally fine. I know that there's a lot of jargon here, but I'm assuming sort of no background, and I'm going to keep everything sort of high level to make it really accessible. That said, I am very happy to say that the work I'm going to be talking about was published earlier this year in Royal Society Interface. So if you're interested in the work, please feel free to look at the QR code. I'm a QR code guy, so there's going to be a few of these throughout. But a lot of what I'm going to be talking about is data assimilation. I'm going to be talking about ABMs. If you're not familiar with those, it's totally fine, as I said before. And then I'll talk a little bit about the results that we have, mostly the algorithms that we developed as opposed to the technical details for our results. But again, this is all easily accessible, and I'm always happy to talk about it. Okay, so to kick things off, I'm going to assume that most people are not familiar with data assimilation. And so for data assimilation, you have two sources of information, right? You have your observations for a target system, imagine a target biological system, and then you have a model, which a lot of us do, right? And so when you're looking at the observations, they're typically incomplete because there's only certain details that you can observe. This is very frequently the case because of all kinds of limitations. And then the observations are also going to be noisy. This is either maybe because of stochasticity that's inherent within the target system, but also instrumentation errors, right? So as some of us have experience with, there might be issues with accuracy, there might be issues with resolution. Doesn't mean that we shouldn't, consider our observations to be good, but we might want to take them with a little bit of a grain of salt, all right? And then on the other hand, we have predictions from a model. Now, the model, as most of us are probably familiar with, is going to be incomplete, right? There's going to be certain details that are missing, either because we've made simplifications, or maybe we had to cut things out for computational reasoning or something else like that. So it's going to be incomplete, and it's also going to be noisy. And that might be because your model has stochasticity, or it might be because through your simplifications, through your details that are missing, you have prediction errors, all right? And so you've got these two sources of information that are both incomplete and noisy. And the idea of data assimilation is you want to take your two sources of information and you want to produce a sort of optimal estimate of the current and the future state of whatever system that you're attempting to model. That's the whole endeavor of data assimilation. Typically, whenever you see it, right, you'll also have this sort of loop situation. So this is this little thing that's going on here. So as you produce a forecast, it might inform your model, and then you repeat this cycle again. Now, as much as I would like to go into the history of data assimilation, let me just say that it is rich. It comes from numerical weather prediction, and there I will say that the models that they're dealing with have hundreds of parameters, hundreds if not thousands of variables. And of course, in a lot of those instances, if you're thinking about like a hurricane model or something else like that, they may have supercomputers, but a lot of the methodology comes from before we had these computational advances. And so, if you're interested in this kind of stuff, if you're interested in incorporating observations into your modeling, I do recommend that you look into data assimilation literature. It is very rich. The way that you can do data assimilation, you've got a lot of options, right? Some people use it for estimating initial conditions. Some people use it for parameterization or personalization, which is the kind of flavor that we're working with here. And then there's also this question of doing it once versus doing it repetitively, right? So in the weather context, typically you do it repetitively, but in our cases, doing it repetitively might be, a little bit less feasible, okay? But so these are the kind of flavors in the high-level overview. Now, the kind of models that I'm working with, for the most part, are biological and medical models, and this whole idea of a digital twin. So you might have seen or heard of digital twins. If not, no worries. The National Academies actually has a really useful report that I have a QR code for here that goes over the details not only of what makes a digital twin, but also a lot of the foundational gaps that still exist for developing digital twins. And so what really makes a digital twin sort of distinct from just like a model that you might have is that it is quote, quote, up to date. So it's going to change with respect to your target system in the medical context with respect to a patient or an organ, and it's going to inform medical decisions. And so really, if you think medical digital twin, or just digital twin, you're looking at this cycle, right? You're looking at the physical counterpart, that's whatever system that you're modeling, and your virtual representation, that's your model. Your model can be mechanical, it can be statistical, it can be AI or ML, whatever your, your preference is. But the idea is that your model is producing something that's going to inform, in this case, in the medical case, decision-making, right? So which drugs to use, which tests to run, that sort of thing. Then there's going to be some kind of change in the physical counterpart, and that change should go back to the model so that the model stays up to date. And that's where the data assimilation portion comes in, right? And so it's the idea that you can do this loop repeatedly. That's what makes it a digital twin. Up until recently, there was a lot of interest from the NSF, NIH, and other federal agencies for funding digital twin research, again, because there's a lot of foundational gaps. There are still FOAs that are out for mathematical foundations for digital twins and that sort of thing, so I do recommend that you look into those if you're interested. But so our context is in particular data simulation for digital twins, which in and of itself is already quite difficult when you get to large models. Now, the tool that we're basing a lot of our work on is the Kalman filter, which is one of these old classical tools for data simulation. It was developed by Rudolf Kalman, and it's actually the primary reason why he got the National Medal of Science back in 2009, if I remember correctly. All right, and so this is a quote, optimal algorithm. It's optimal with respect to minimizing the min squared error of the estimates. This is actually a visualization that I pulled from Wikipedia. And so the way that it runs is very similar to the flowchart I had before. You start off with some prior knowledge of your state. This might be some prior estimate. This might be some initial observations. Sort of take your pick. You'll run your model. That's the prediction step. And then when you go to actually make an update, this is where the measurements can come in. And that's where you're going to predict and update both the estimate means and the estimate covariances of your variables. And technically, it's really your variables and your parameters. So you're updating everything all together. And then you continue this cycle through. I will say that there's a sort of key assumption that's necessary for the optimality of the algorithm. So it assumes that all noise is Gaussian, which, I think for a lot of us, we sort of recognize that Gaussian is kind of like an ideal, but very infrequently what we actually tend to find. If you're doing biology, maybe it's one of the things that you might assume right off the bat until you start encountering data. But so I do want to mention that that's present. On the other hand, though, we do have some advantages. So one of the things that is nice about the filter is that measurements can be irregular. I know this sort of seems like you're kind of doing this periodically, but really the way the filter works is you'll be running your model and producing updates, and then as soon as you get measurements, those come in, and that's when you actually run the filter. The other nice thing that I don't have listed is that your measurements can be incomplete. And this gets to the idea that we can only observe certain things. So the filter still actually works and still produces updates and everything else like that, even if you have a partial idea of what's actually going on in your system based on your observations, okay? Traditionally, Kalman filters are used in differential equation models, and there's a lot of classic literature that goes into those details. With integrals and all the other fun things that a lot of us do. I will say, however, that if you have a discrete model, which are the kind of models that I'll be talking about, it's actually possible to do a lot of this with linear algebra. And so just because you have a discrete model, it doesn't mean that you can't do the Kalman filter. In fact, it actually makes it easier to some extent. And if you want to talk about those technical details, I'm happy to talk about it, but this is something that's open to us. Now, because of those assumptions and everything else like that, there's actually a lot of flavors of the Kalman filter. There's the extended one, the unscented one, ensemble, yada, yada, yada. There's a lot of variations. The one that we use is the ensemble Kalman filter, and I had a whole spiel prepared on why you should do ensemble modeling, but thankfully our first speaker for today talked about all the advantages for ensemble modeling anyways. So here I'll just mention as a sort of like reminder, my little 2 cents. If you take nothing else away from the stuff that I talk about, I do recommend that you consider ensemble modeling within your work, regardless of whatever kind of modeling that you do. This is a good way to take into account the problems of parameter identifiability, the problems of just estimating parameters in general and everything else. So in our case, for the ensemble Kalman filter, what we're using, the ensemble is not only because we have a lot of parameters, but also because it does make a lot of things computationally tractable. And the idea of what it spits out, it's almost like a probability distribution. And so if you've ever seen like hurricane weather forecasting and everything else, and you have this sort of cone of uncertainty, this is the kind of thing that you have in mind. The truth should be somewhere within this range, this like almost confidence interval, okay? All right, so that's the main tool that we're gonna be using, and we want to apply the Kalman filter to stochastic multi-scale models. The ones that we choose as a relatively general modeling scheme called an agent-based model. If you're not familiar with them, agent-based models in general are sort of computational models where you have agents that are governed by local rules and they're interacting with one another. And what you typically want to do with these kind of models is see how the system is affected overall in terms of pattern formation, in terms of just other types of emergent behavior, okay? I've got an example over here. We don't have to worry about the technical details associated to it. Suffice to say that there's a whole bunch of little dots and stuff. Those are agents that are moving around, interacting with one another. There are ones that are being born, that are dying out. And so when you look at this kind of modeling system, typically it's stochastic. This is on purpose. A lot of people who develop ABMs want some kind of randomness, some kind of stochasticity because of whatever biological system that they're attempting to model. And it's typically multi-scale. And so what I mean by that is that there will be rules internal to the cells, the agents. They can be cells, which might be differential equations. They might be Boolean networks, take your pick. There are rules that govern the sort of intracellular, intercellular interactions, but there might also be like high-level rules in fact affecting the environment as a whole. So there's different things happening at multiple scales. What this results in, though, is a really variable state space. So you have agents that are being born, that are dying out very frequently. So the finer details for your state space are changing from one time step to another. For our purposes, we found it very useful to kind of think about the state space across two levels, right? So we'll think about the microstate space. That's going to be your fine-grained type of description, and it's describing everything. So it's all the variables, all the attribute values for every single agent at a specific point in time, keeping in mind that the model may have a lot of parameters and that your state space, in this case, might be changing from one time point to another, as I said before. Then you have your macro state space. So this is a much higher, coarser description, and it's typically a summarized description of things across your entire model. So maybe agent counts or maybe concentrations of, whatever biomolecules you have within your environment, that sort of thing, okay? We think about the macrostate space not only because it gives us an ability to sort of exist in a fixed dimensional state space, but also because that's usually where our observations live and exist, right? So especially in a medical context, we're probably not going to know exactly where every single cell is for an environment, for a patient within an in vivo environment, but we might know the concentrations of various cytokines or the concentrations of like a pathogen or something else like that from a blood draw, something of this sort, right? So this is also part of the reason why we wanted to think about the macro level. And so on that note, our first and sort of like big contribution, one of our two big contributions that we introduced in this paper is what we call the ABM Kalman filter. And so this is allowing us to produce updates using data assimilation, using the ensemble Kalman filter in particular, on an ABM. And so I'll sort of go through this toy example that I've got here. So the first thing that we have is the prediction step. So this is going from t to t plus 1. As I mentioned before, we have an ensemble, so it's not just one simulation that we're running. Here I've got 2. In general, I might have 50. That's what we tend to do for our ensembles. So you just incremented one, so that means you're running the model, and then you go to your update step. So at this point, you'll summarize, you'll go up to your macro level. Here in this toy example, we've just got agent counts. You might have other aspects that you're capturing. And then if you have measurements, you might not have measurements. If you have measurements, that's where you run the ensemble Kalman filter. And just as a reminder, right, so your measurements might be incomplete here in this example. Maybe we only have information on the yellow ones. So we run the filter and we're able to get a new ensemble of macrostates that we say these are a much better representation of what this true system might actually be doing. And then as the final step, we go down from the macro level to micro level to run the model again. Now that part is actually very suspicious. If you really think about it, right? So if I've got a microstate for beforehand and some kind of summary that I want to hit a target for, right? How do I know how to pick a new microstate? In general, this is just a terrible problem to try to tackle, right? If I've got this vector from my macrostate and I'm trying to match it with some update, if I look at the space is gigantic. I mean, it's even difficult to sort of define a good metric in general for what the space looks like. If you're looking at an ABM, you have to start making calls of like, what is a better version? This one seems to have a better geometry versus this other one. This one doesn't seem feasible, but then how do we make those kinds of calls? And so while this algorithm that I'm mentioning here at a high level is our sort of first step, the next thing that we realized we needed to tackle is how do we actually do the synthesis step in order to complete the loop and continue the process? And so that's what I'm going to be talking about basically for the rest of this talk, how we actually made a choice for each simulation that we thought was good and generalizable, not just for the ABMs that we considered, but hopefully for the ABMs that other people might be interested in, both here at the conference and in general in the math bio community. Okay, now, we considered 2 ABMs. I'm just going to point one out. I'm not going to go through the nitty-gritty details of everything that makes the ABM run. This is a published one, so it's not one that we developed. It's of viral infection. We've got 40 plus parameters, 20 plus state variables. It's large, and it has all sorts of parameter identifiability issues. It actually is doing a simulation of tissue and immune response with respect to viral infection. And so what you have running around here are immune response cells, and you have the epithelium that is healthy, it's infected, it's dying out and everything else. And I know this is probably a bit difficult to see, but what we have in the middle are actually concentrations of various biomolecules. So maybe the virus, maybe various cytokines that are being released from the immune response cells, and then these things in turn diffuse as diffusion actually goes. So that's a portion of the simulation and everything, okay? So this is the ABM that we wanted to work with because it's already out there. It's biologically based on, actual experimental results and everything else. And it's the kind of thing that we were thinking, okay, if we want to tackle this problem, let's try to tackle it where people actually are instead of choosing a very simple toy example. All right. Now, in order to tackle this, what we decided to do is employ a technique called quantization. If you're not familiar with quantization, in general, it is the mapping of a large set to a small set. So you're mapping from one set to a set that is smaller, let's say smaller cardinality, okay? So a simple example that you might have in your mind is you're going from the real numbers to the integers, and maybe you're just rounding, okay? So then what we have is what's called the quantization error. This is your rounding error, the thing that you lose by going down. Now, rather than show you all the technical details about how we actually employed this in our work, I thought, let's go with pictures. Okay, so this is a representation of the Mona Lisa, presumably in all colors as much as it can be. And let's say that the problem that I have is that I want to represent the Mona Lisa in black and white. So maybe a first thought that I would try to do is say, set a threshold and say, okay, if it's above this, it's going to be black. If it's below this, it's going to be white, or whichever direction you want to go. The problem with that approach is what is called bounding. So if you try to do just rounding in general at a pixel level, you're going to lose a lot of the spatial information. So each pixel has been mapped to its closest value in the 0, 1 sort of setting, black and white sort of setting, but I don't really see a lot of this background. I don't really see a lot of her features and everything else. Okay, so an alternative to this is what is called error diffusion. And the idea for error diffusion, what I want you to think about is that you're going to scan through and you're going to be making choices on what you should be switching your pixel to, either black or white. But as you accumulate error, you then diffuse that error. And then eventually you have to make up for that diffusion error in other pixels that you have. And so if you look at this bottom picture over here, still black and white. Some of the pixels in her hair, for example, are white, right? So some things are technically wrong. They're not being matched to the closest thing that they should be. But the overarching effect is that you can actually see a lot more of the features. You can see the river. You can see a lot more of her clothing and everything else like this, okay? So you're able to recover a lot more of the spatial quality of the image, even if on a pixel level, you still have some errors. And for our purposes, that's totally fine. Now, I do want to mention that, there's nothing special about going to binary, right? We could have chosen 8 colors. So on the top, we've got this not so flattering picture that's on 8 colors. And then on the bottom one, we have an 8-bit representation, which I would say is a pretty close representation of the colors that we actually see within the original picture. So this is the kind of thing that we wanted to employ to do this synthesis. But how do you actually do that? So again, just from a high-level non-technical perspective, I'll give you an example. Let's say that we're increasing the number of healthy cells within that ABM that I mentioned earlier. all right? So in this case, we've got continuous variables and non-continuous and discrete variables within a lattice. For the continuous ones, so these are your biomolecule concentrations, you're just going to scale. So if it needs to increase by 20%, you just multiply by 20%, you have an increase across everything, right? But for discrete ones, this is where you have to be a bit more careful. So imagine that you have one single cell that can exist within a lattice, and you have to increase the number of healthy cells. And so this is where we do scaling, right? So let's say we have to increase by 20%. We just increase all the cells that are healthy already. So now we have 1.2 cells that are healthy on the environment, and then we quantize. And so this is bringing it back down to, let's just see if I can choose a pointer. Hey, there we go, okay. So this is that scanning that I mentioned before. This is where all the healthy cells are currently. And what's happening here is that I'm distributing the cells so that they're close to where other healthy cells already are. So if I go back to the beginning and if I see these two holes, right, then when I go scroll forward to the end, those holes are filled up, right? And so also if you look at the borders for where the healthy cells already are, those things are getting fuzzier. So it's this type of approach that's respecting the geometry to a certain extent while also making the modifications that you need. And you can do this in the upward or downward direction as is necessary. Now, a few things. So the process is deterministic. In our case, we chose left to right, top to bottom. You can make other choices. I don't want to say that it doesn't matter. It might make slight variations, but that's something that you can consider. Obviously, you can make this non-deterministic. For our purposes, we didn't find that to be necessary. And in fact, it was kind of advantageous to go deterministic because now we can choose one specific microstate that our macrostate should correspond to when we're doing the update, right? So now we have something that is being matched to directly. Now, this is showing for the healthy cells, but the reality is that we're doing this simultaneously for all state variables, and again, for all parameters within your simulation. So this I'm almost sure you can't see, especially if you're further towards the back. But we're doing a scan. We're doing that scan that I showed before. And so one of the things that I'm showing here is that the locations should be changed, right? The number of empty lattice points should be changed, the number of infected, dead. For their purposes, they also distinguish dead versus apoptosis. But the idea is that we're making these changes all the way throughout while we're also changing the continuous variables. And so what we end up with is a full change. The video is actually much larger than this. And so Adam put it up on YouTube. So there's a QR code for the YouTube if you're so interested. But that's the idea that we were working with here. So now we have something that we're ending up that's deterministic for microstate synthesis. Now, what I didn't get to is like actual evaluations for how well we did. Let me just say at a high level that we found our methodology is much better for improving model predictions than as opposed to when you don't do data simulation. The main thing though is that this is really, as far as we know, the first sort of step towards doing data simulation for spatial ABMs, for ABMs where you really need to pay attention to the spatial context. So again, the QR code for our publication that's out already. We've got the algorithm that allows you to do the Kalman filter for data simulation. And we also have what I hope is a very generalizable algorithm for other people who are developing ABMs. And then the other thing that I will mention, what I'll say at last, is that there's a lot of avenues to improve or generalize our work, okay? So what we did to some extent is the first step. We've got a lot of edge cases that we are considering how to handle. And then there's also a lot of alternatives for microstate synthesis. We've sort of proposed one, but we're already thinking about alternatives that maybe use stable diffusion or other sort of AI type of techniques. I also do work with topological data analysis, so we're thinking about that. But if anybody's interested in this work, I'd be very, very happy to talk to you. So please feel free to reach out. And with that, I will say thank you for listening.
We have time for questions.
Thank you for a great talk. So earlier in the talk, you mentioned that you like ensemble models. So I'm wondering if you can apply that, when you do microstate synthesis, would it be a good idea to synthesize an ensemble of microstates rather than just pick a particular one?
Yeah, actually, so in general, that's what I would recommend. So one of the things I should mention that we were originally considering, other than the Kalman filter, for example, was like ABC, approximate Bayesian computation, or like AABC, if you're familiar with that. I know that you are, but if other people are familiar with that. And the problem with a lot of those other types of techniques is that they tend to be very computationally heavy. So here, we can have an ensemble that's covering a lot of things and running a lot of simulations, and it's still able to produce these sort of updates. So absolutely you can, even if you're not, I should clarify, even if you're not using ABMs, you can still use these techniques, right? So yeah, so I would absolutely recommend that sort of thing for microstates, if I understood your question correctly.
Other questions?
Hi, really interesting that you're considering using diffusion, latent diffusion, or AI methods to try to generate the macrostates. They might be very computationally expensive, but what would be the initial state in that case? How would you initialize those algorithms?
Yeah, for sure. So this is where we get into the bonus slides. Okay, so this is probably very difficult to see, so this is something that we put in an NIH grant proposal just recently, and then the part that we're talking about here is using, in this case, stable diffusion to do microstate synthesis. And so one of the nice things about how we've optimized the ABM is that we can generate a lot of states fairly cheaply. I say fairly cheaply, maybe it takes a few days to generate a few hundreds of thousands, but now we've got a lot of those snapshots, and so we consider those snapshots to be the sort of realistic microstates that we might expect to find. And so now we have, if you're familiar with it, the ability to go from synthesis to try to approximate. Oh, well, I do promise that there was a picture that I was showing. But anyway, so this is how you're able to potentially do the stable diffusion approach. Oh, okay. Well, there was a picture there, I promise. But yeah.